cybersecurity space for 11 years. Through a career as both an analyst, incident responder, pen tester, and red team operator, he has a holistic view and experience set within operational cybersecurity. Trym holds a bachelor's degree in software engineering and the OSCP certification, among others. His talk today is called Shellcode, what it is and why it's loved by cybercriminals.
No, I don't need it. All right. So yeah, as you can tell by the template here, I work at SpareBank as an incident responder. That's about all the time for introductions I have because we have a lot of shit to get through. So, what is shellcode and what is it used for? How do you write it and how do you use it? So, Andre luckily sort of covered a lot of this already. So, you use shellcode for, among other things, defense evasion, but like the core concept is you want to run malicious code, right? Or at least that's what I use it for. So we're going to get into how to write your own custom shellcode. Very like dumbed down, simple way of doing it. Not as advanced as Andre would do it probably, but still it's easier to grasp the concepts when you do it this way. And also, how do you use it? I'm going to show you like a dead simple shellcode loader and just describe the sort of basic principles. So, what is shellcode? It looks like this. You've probably seen it if you've played with MSF Venom, for instance. Shellcode is also called position-independent code, meaning it should be able to run from wherever you put it, like with certain exceptions, of course. Through my research for this talk, I basically figured the simplest, most concise way of putting it is this is just assembly in hexadecimal form. So you're encoding assembly to hexadecimal and then running it. That's the gist. So think about what a compiler is actually doing. You're writing some Hello World C code, you compile it, it will convert it to assembly and then to machine code that's runnable by the CPU. So if you compile this program, open it up in a debugger, you'll get this assembly code here. And the individual assembly instructions like move and push and call and RBP, RSP, all these registers, you convert this to hex. So for instance, the move RBP, RSP instruction will be 4889E5 in hexadecimal. So you prepend that with a \x and you put that in memory and you run it. That's like the very, very basic way to put it. And don't get confused by this. This is memory addresses, not like the actual shellcode, just putting it out there. So, what do you use it for? Well, like already mentioned, you run malicious code to get a foothold on the system, for instance. You might want to run certain actions from a specific process context, like say you want to dump cookies or something. You might want to do it from a web browser context and not like Teams XE. That might flag something for blue team to look at. You can also run it as defense evasion, so you don't want to put your malicious code on disk for static detection purposes. You want to run it in like a memory enclave that looks legitimate. That might be like the two best uses for this, I think. And when we write shellcode for Windows, we have a few considerations we need to take into account. So referring to the fact that it's position-independent code, it should be able to run from anywhere, right? And if you look at like the first illustration here, which is the PE file basic structure, you have some headers, you have blah, 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 section tables, and then you get to the sections. Now your assembly code will usually be located in the .text section. And if you look at the example from earlier, you can see that when I define a string, this ends up in like a .string hello world sort of reference to a certain section of memory. This is because when I define the string, it'll be placed in the data section, most likely, I think. So the assembly in .text refers to memory space in .data. And what we're trying to do is take the assembly from .text, run it from anywhere, which means if you do that, it will refer to memory space that doesn't exist in that context. So we need a way to counteract sort of that part that the data will be saved in data for reference by .text. So there's a nice little neat trick to that I'll show you later on. But that's one consideration. You also have Windows process architecture, which brings with it many other different stuff you have to figure out. So consider the process architecture under Windows. So disregarding the kernel space stuff, we have thread environment block and process environment block in the user space. Seeing as the code will run from anywhere, you can't just import stuff like you would when you program normally. You have to sort of figure out where the different methods you're going to run are, because if you're programming without methods, it's like pretty limited what you can do. But if you want to run methods, there's a technique called peb walking we're going to go through. So in like basic terms, you're going to find the process environment block in memory. You're going to go through the module list. This is like the last illustration here is the architecture of the process environment block. And one important part here is the module list. So the module list in the process environment block will contain all the modules that your given process has imported. So for instance, some random program I just wrote and compiled and ran will load itself first as an exe. It will then load most likely kernel 32 and then ntdll.dll, which are sort of providing the basic Windows functionality. So if you find this list, you can iterate through the list, and then you can figure out where in memory is the copy of that DLL located, so I can utilize the API calls that it has. That's sort of the gist. So you have to account for both the variables in assembly, and you have to account for where in memory you can find the methods you want to use. So how do you do that in practice? When you do peb walking, or there's probably a million ways to do it. I'm not an expert, but the way I do it is you use a flag called GS, and GS is a pointer to the base of the thread environment block. Now, there's a method for this in basically all compilers that will this will be like intrinsic to the compiler, so it's always available to you, even though you take the assembly out of its original space and put it somewhere else. So if you use that, you get a pointer to the base of the thread environment block in your user space memory. And then if you add 0x60 as an offset to that pointer, that will give you another pointer to the process environment block, which contains the module list we want. So that's peb walking basically confined into 2 minutes. And then we want to get from that module list, we want to find the appropriate DLL. We want to find get proc address, which is a nifty little method in kernel32.dll. And get proc address allows us to find the memory address of any other method. So it's like you have to go through a little bit of hard work to get proc address, but once you have get proc address, you can find anything else basically. And using get proc address, I'm going to find winexec, which is exactly what it sounds like. It's a Windows method that executes things. So keeping this like short and sweet, we're just gonna pop calc.exe like any true lead hacker does to show that they can run code. So how do you then take this shellcode with all your nifty tricks and then use it? Like Andre mentioned, you want to use a shellcode loader, and the objective of the shellcode loader is just take your shellcode, put it in memory, execute it. That's it. And of course, you can do encryption of the shellcode or obfuscation rather to defeat certain detections and stuff. But I've basically chosen to leave all that out. I want to focus on the core principles to be able to explain it better. So over to the demo, which is running on a remote ESXi. So this is going to be fun. Come on, please. Oh. Oh, it's working. .gif. Yes.
You have to activate Windows for that.
Yeah. So let's here consider my shellcode, or my almost finished shellcode. So just going through the code real quick. We declare a no inline method. As far as I understand, this is just to keep the size of the assembly down because you have limited space to work with. And then we declare a H module to kernel 32. So we're gonna store the address to kernel 32 in memory in this module or this variable later on. This is the fun part with the GS thing I talked about. So you have a method under Visual Studio. It's __ read GSQ work, and then you can supply a offset. So if you run that method, supply the offset, then you can typecast that to a pointer to peb variable. You have a pointer to peb. So, okay, now you have this as a baseline, and then we can start working with that. So to find the kernel 32 entry in the module list. The module list is a kind of a fun structure because it's a doubly linked list. So you can do, if you go to the pad, and then there's a pointer to loader, and then from loader, there's another pointer to in-memory order module list, which is the list we're looking for. If you go flink, 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 it's not because you're good, it's a forward link. Likewise, if you wanted to go backwards in the list, it's blink. So backward link, right? And like I said before, the exe will first load itself, and then it will load kernel, or actually I said it wrong. It's first itself, then ntdll, and then kernel 32, which is why we have 3 flinks, because it jumps 3 times through the module list. So then you have a pointer to the third module in the list, which most likely will be kernel 32. So we have that in kernel 32 entry. And then you can parse the headers for this. This is just like groundskeeping and red tape to be able to use this structure later on. So if I go down a bit, we have some more code. So now you want to create a pointer to the methods exposed by kernel 32. So it's like you're going to one pointer to a list and then sifting from the list, and then you have another list entry, and that has another list again. So it's like insert the meme of that guy from, like, is it Arrested Development or something, where he's like, yeah, bloodshot eyes and going insane. In there, you want to find, yeah, the exports table, and the code is too long here, but you're basically saying, yeah, after the headers, and there's a pointer to a data directory where there's a list. If I scroll, maybe we can see it. Maybe we can't. I guess we're gonna have to do it the hard way. Don't you love Mac and then Windows in a VM? Jesus Christ. I realize this is bad presentation technique. I'm really sorry.
You do have a scroll bar at the end.
Yes, but then it might get mad at me. All right, you're gonna have to take my word for it, right? There is a list there. And then you wanna parse what you found from the exports table. So you have an address of functions list, and address of function names, and address of name ordinals. And like the function address and names, it's pretty self-explanatory. The name ordinals is like some kind of initials for each method. I'm sure Andre could explain this way better than I can, so you find him afterwards. But basically, we need these lists to be able to iterate over them and find what we want. And now, once we parse the header, we can take our previous kernel 32 method and just assign the address of that to this. We're going to use that later once we finally have the get proc address method. Now, remember the string stuff I talked about, that it gets put in different sections and all that jazz. One nifty trick to sort of beat that is create a struct of unsigned integer 64 values, and then you can make as many as you want, but beware that each uint64 can hold 8 bytes. So you split the string you want into 8-byte chunks and assign them to T0, T1, T2, and so forth. And later on, you can just refer to the start of the struct, and that will be represented as a string if you typecast it to a string. So it's a pretty fun trick. I'm going to show you it afterwards. And then let's go down. Now we're going to do some more preparations because we're going to load methods that we're going to use, right? So we basically create our own types, our own like data types. So we just emulate the get proc address and winexec types, like what kind of arguments they take with the correct type and what kind of return values they have. And then we create variables based on our types, just set them to null pointer for now, and then we're going to assign the addresses to them once we find what we're looking for. And then it's a simple for loop to loop over the kernel exports table as number of names. So you loop through that, and for each iteration, you check against, let's see, I'm going to scroll a bit down so this is easier to see. This is what I was talking about with the strings. So if you basically take get proc address, paste it into like cyberchef, you will get these bytes that are representing each letter. So these are the first 8. And luckily, there's no other method in that export table in kernel 32 that starts with get proc A, because that's what we're going to compare based on. So you take that value and you need to account for a little endian. So that's why 41 is first and then 63 and so forth. And then you're going to do, for each iteration, do a check for the current name, if that is equal to get proc A. And you can see we typecast this to uint64 to get a comparison that is actually able to compare. So if that matches, that means you found get proc A or get proc address in the list of name ordinals from kernel 32 exports. So then it's more or less just assign this to our get proc address that we defined further up here, typecast it to our type, and then it's some mumbo jumbo to get the actual address of the actual function that we're going to use. So assign that there. Now, then there's some more fun stuff. Once we've done that, we can now do basically the same thing with winexec, which is the method we're going to use to pop calc. Now a quick quiz to make sure you're awake. Why do you want to have, since this is only 8 characters long, you could contain this in like just T0 with 8 bytes. Why do you want to end with zeros?
String uses null termination.
Good boy. That's correct. So
Repeat that, sorry?
the C strings use null at the end to terminate the string.
Yeah.
So if it was no zeros here, it might be that in that memory there's still other characters, meaning the string would just continue. So it would be winexec blah 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 going on for ages until it reaches a null, and then it ends the string. So when I like here, I cast the content of that struct to const char pointer. If there wasn't a zero, it would just continue on until it found a zero, which would make a really good string to be useful. So, and then we use the nifty get proc address, just point it to kernel 32, say I want to find the string winexec in kernel 32. It returns a memory address for you. You just assign it to winexec and typecast it to our type. So now you have you walked the peb, you found the method you're going to use, and you assign winexec to the method. Now we're going to do the string trick again with calc.exe, and then run winexec to run calc.exe. The 5 here is just an option that winexec requires. I believe it refers to show the window and not do anything else. So now you might wonder how the hell do we get this in assembly and bytes? So you can enable some options in Visual Studio that I don't have time to explain, but it's very easy. It's contained in the tutorial I have a link to. So you might have noticed I set a breakpoint on the top of this method. Then when you run the debugger, it stops at the breakpoint, and now it has compiled all the C code. So if you go over to the disassembly tab, we can see here we have our, since I've enabled the show code bytes, you have bytes for every single assembly instruction. So if we now take all of this, every single part until we get to the return here, copy that. And I am short as hell on time, so I am going to try and do this quickly. We take this into a text editor. I have a cheat sheet, and we do some regex on this. Do this, paste this. Just, oh Jesus, I lost the pointer. There it is. No. So, and then we want to get rid of all the white space and all the line breaks. Now we have one huge blob. We're going to prettify that a little bit. And hopefully I can do this under 5 minutes.
No pressure.
No, no pressure, not at all. $1 to get the first capture group, and then line break. Yes. And now we want to prepend with our \x. So, like so. Oh, Jesus, I did it twice. Oh, Lord. There we go. Nice. And for the final trick, we're going to add parentheses on each line start and line end. Like this. See, hacking isn't as sexy as they make it out to be. There we go. Okay, so we have shellcode. Now we take all of this. We open up our loader. How much time do I have left now?
Couple of minutes.
Couple of minutes. Okay, we can work with that. And so this is like a very basic shellcode loader. So you'll see the shellcode array is empty. Basically it does what Andre says. It allocates memory space based on the size of the shellcode. It then writes the shellcode from that buffer to the memory address we just allocated, and then it runs it. And this line here, I didn't understand for like years and years until I actually Googled it. And so you basically treat the address of the shellcode as a function, and then you typecast it to a void pointer function. And when you put the parentheses at the end, it will implicitly say, this is a function, please run it. That's the short description. So if I, just for demonstration's sake, I'm in the loader, say, we'll build this. No. God damn it. Okay, it's already built. Now it should run, and I will. Now that was premature because I forgot to build it after I deleted the shellcode after I ran this test yesterday. So just to show you how this this should work, if I do this, maybe it's easier to hit build.
You're building empty
Yeah.
shellcode?
Yes, empty shellcode. That's the point.
Oh, yep.
Yeah, because I want to show you what happens when there is none. It just says meh, and then if we do no, for fuck's sake. There we go. last exit code, it'll give you some crazy number because you triggered an error, you tried to allocate memory that isn't anything, it doesn't like it. So if we now do this, place the shellcode in here. It puts the lotion on its skin. No, okay. So we have to copy this again. I have to find the mouse pointer again. And we put it in here. There we go. Save that. Build. Solution. And hopefully it went as well as it did earlier. Yes. Nice. And now the exit code is 0 because it finished. So super quick summary. I know I'm out of time. Shellcode is assembled in hexadecimal form. It's position independent and can run almost anywhere. You can do some Windows internal malarkey to call the APIs you need. It's often used and loved, as is the title of this demonstration, used by criminals to run malicious code and evade defense. And it's used in conjunction with a shellcode loader that can be written in insert your favorite programming language. These are some sources. Yeah, old ChatGPT, putting in work. Thank you for your time.
Right. Thanks to Trym. This is the end of the last segment, and now it is time for lunch. So, have at it.
We're going to start back at 13:15, so back in the room by then, please.